I did promise multiple times that at some point I was going to go back and clean up my old Overture levels. Overture is a mess. It's the first computer architecture we've built, and yeah, you can just see how it's not particularly streamlined, and neither are the programs we wrote for it. And I do want to go back and clean everything up. So that's the plan for today. However, I decided to add a bit of a twist to this. And having recently enough, completed division, and having created both an algorithm for division and a single tick solution for division, I think I might want to apply a similar principle to some of these previous levels. And instead of using a generalized architecture like Overture to add 5, I can very easily and very cheaply solve this level with a specialized circuit. And that's what I intend to do for some of these. I still do intend to build an improved Overture, and overall, I think using specialized circuits, especially for levels like add 5, is kind of cheating a little bit, because we could add 5 all the way back before we built a working computer, but what add 5 really teaches us is the very basic first steps of how to use the computer. And yeah, I do think these levels are necessary, and you should at least solve them with a Turing Complete machine at some point. But now that I have actually solved them, I have completed them with a proper architecture, I think it would be an interesting challenge to try to make specialized components for some of these. And I think some of these might actually be interesting, like the maze. Could I make a specialized component that implements this? No, it's not 30 bits. 16-bit program. Could this be doable with a specialized component? I'm not sure. I'm not sure I'm even going to try this. It depends on how the other levels go. But yeah, even something like this, I don't even remember what this is. I expect these levels to be a bit of a challenge. And yeah, I think that's going to be more interesting. So with that out of the way, let's get started. So yeah, at this point we get a working computer, and the first level is add 5. I am now free to change the program of my computer. Yes, I am also free to use a new computer. So let's keep Overture, and let's let me organize this a bit. Okay, so I made a directory tailored, and we're gonna put tailored architectures into here. So right now what we need is add 5 to the input, and I expect this to be a absolutely trivial task, except I need to create a custom const +5 adder, which you've seen a million times by now, so I'm also gonna do that off camera. So here we have our +5, as always, +1 here, +1 here, and then carry as necessary. It's fairly cheap. In fact, I think this is the cheapest it can be, probably, in terms of gate score. Maybe delay score can be improved. But, oops, I'm out for some reason. Let's go back, add 5. So what I need to do is I need to go into my +const, take my +5, and wire everything together. And then I think I can safely enable both inputs, input and output, like so. Let's test. Yeah, success. How do I want to make this a bit more neat. Something like this. Sure. Perfect. So we now have a ridiculously low gate score and delay score and tick score. First test scored. Okay. Calibrating laser cannons. Again, we're gonna go down from gate score 761 to something much more manageable, but I have no recollection of what this was. So let's take a look at the task again. Naturally shoot incoming asteroids with lasers. Calculate the circumference of the asteroids using an advanced equation. You can approximate pi as 3. So what I need is... yeah, sure. You didn't exactly tell me what to do. Or did I read it wrong? Oops. R is the input, okay. And what I need to do is I need to multiply R by 6, right? What do I do here? Yeah, I add 3 6 times. Or, sorry, I add the thing to itself 6 times. Huh. I wonder if it would be cheaper to do this kind of addition chain, or it would be... Well... I could put it in a register, honestly. I could put it in like a counter, which just adds to itself, and use a couple of ticks to do the addition, but save on the gates. I think that would be a decent solution, right? So this is going to be laser cannons. Cannons. How much is multiplication? Math, multiply. No, multiplication is almost as expensive as Overture itself. So yeah, I think what I actually want to do is I want to take a full adder, an 8-bit full adder, math, addition, and then, yeah, I will want to add the thing to itself. This is interesting. So let me. I'm immediately thinking of I could, for example, I could get x plus x is 2x, but then I could do 2x plus 2x to save on ticks. This is going to be a bit difficult to wire. So let me just consider this for a moment. Well, this I think is perhaps the simplest solution. So we have one adder, this is 2x, right? X plus x, 2x. Then we have 2x plus x, this is going to be 3x, and then we multiply x by 2, and that's what we get. I do wonder if... Yeah, actually, 2x... Oh... You know what? Yeah, so this will work, but I can improve this significantly, and I just realized. Yeah, this works. But this is not interesting. No. 2x is shift left x. I do have a custom shift left component. Wherever that is. Shift left, yes. So shift left by 1, shift left by 2. So this is times 2. And I do have another one. Shift left by 2. This is times 4. So what I actually need to do is I only need one adder in 2 shifts. Right? So this is already a major improvement. Right? Like this. So that's good. Let's see if this still works. It does. But now, do I really need a full adder? No, I do not. I can make a specialized adder as well, because I know that my inputs are shifted and I do not need to worry about some of the bits. So, do I really want to do that? Why not? I've done so many const adders that I think this should be simple. So I'll be right back. Something along these lines. You've seen this a million times. It's one of these again. So success. This cost us a single tick, and this cost us 54 gates. So yeah, that's pretty cool. I do expect this to get a lot harder in the next levels. Okay, storage cracker. Yeah, this is gonna be more interesting. I remember this one, kind of. So again, let's switch schematic, tailored, new schematic, storage cracker. What is the problem statement here? The door keeps changing the passcode. We need a program that can recover the passcode at any time. The easiest way to find the passcode would be to try all combinations until you find the right one. Although the broken mechanism does make a weird beep. Aha. Okay, so I see. So the easiest solution is going to be 8-bit counter here and on. This is just immediately solved. No problem. However, I do recall that for my original solution to this, if I switch back to Overture and I take a look, which, by the way, where is this program saved? That's weird. Yeah, for my original program, what I did, yeah, these are very good comments. These are very good comments, but I can make this a bit more neat. Yeah, so what I do is, I'm not sure what I'm doing here. SB says SBB. No idea what this is, but the comments are good. I keep increasing by 15. So I search up until I find a... why is it 15, by the way? Why not 16? 16 sounds more... I remember I came up with this using a quick formula. But 16 sounds more reasonable than 15. Yeah, so I keep increasing until I overshoot. Right, so that's 15. And then I keep decreasing by 1 until I actually reach. So that would be a cheaper tick score, much cheaper. But I wonder if that would actually be worth implementing in hardware. Also, I wonder what the actual name for this is, because there must exist like specialized hardware components. You know how you have a GPU, which is of course commonly used, but it is a purpose-made piece of silicon which cannot perform arbitrary computations. It performs, well, maybe it can perform. I'm not sure. Is a graphics card Turing Complete? I don't know. But yeah, it's tailor-made for a specific purpose. I wonder if there's a name for this, because there must be a lot of these kinds of circuits out there. Okay, so increase by 15. I can do that. I can do that, no problem. Then how do I would need to... Yeah, I would need a mux on my... Oh, wow. Yeah, this is a bit interesting because... actually, you know what? Yeah, I think I have it. I think I may have figured it out. So what I would do, this is gonna be probably easier to draw actually. So what I can do is I can have a plus 15. I have a minus 1, right? Then I have them muxed, right? So mux. No idea what it looks like, right? And then loop back into here. Actually, no. I would have them switched, and I would have the input to them muxed. No. Yeah, no. This is okay. It's this way, and then it just goes straight. But this mux is decided by my input, right? And once I have received the 1, then I switch to this. I will need to remember the 1. Actually, the 1 will always be part of the... So this is... Yeah, so long as I am... As I have overshot, I need to decrement by 1. And unless I have actually hit my target, it's gonna give me a 1 again. So I think this is gonna be very simple to implement, actually. And pretty efficient. Except I need to implement a plus 15 adder. But yeah, I've done so many of these. I keep making more, so why not? Storage cracker. Let me make a plus 15 component. Actually, plus 15 is going to be much more expensive than plus 16. I wonder if... can we just test this real quick? If I switch to Overture and I run this? Oh, I cannot run it. Oh no. Okay, but I think I should be able to... Do I have a MOV here? Yeah, I have a MOV. Can I adapt this? MOV from D to B? What is SB? I have zero recollection of these assembly instructions. So MOV from A to C I can do. What is SB? B. SB, SB. SB. What on earth is SB? So I have N, it's direct, it's in immediate mode, right? This is directly loaded. But then I have... Okay, it's loaded. I put it into C for some reason. So N is in A. Then I put it to C. And what do I do? What do I want to do then? Is this output? Is this IO? 2D is B sub. Where's IO? IO. Out. So maybe out from B? I don't know, let's try. Out from B. Out from B. And load byte, yeah, I think out is gonna be, this is gonna be in or something. Do I have in? Yeah, I have into D. Let's try. Just a guessing game, honestly, but from A to C, this is not well commented. From D to B. Save byte out from D. It's not... I don't think it's working. Yeah, I have zero recollection of how my overture worked. What these instructions were. Okay, what I'm gonna do is I'm gonna go back to my video, take a look, remember, and I'll be back. Okay, I think I figured it out. It's pretty simple. I used to have, well, what I tried to do is I tried to do out from B, and that was all. But the change I made is actually more like leg in this regard, and I have mov from B to out, so out is already a register, except even though it looks special, it's just a register. And I think out and in should be the same thing. Yeah, out and in. Out is 6 and in is 48. Okay, no, it well, it's a single byte instruction, so yeah, that makes sense. Whatever. The point is, this now works, I think. Yeah. And let's see what our tick score is with N15. We get 175. Let's try N16. 246, so 15 is more efficient. Let's try 14. 176 with N14. I am a bit worried because this rates me on the first test. N14. Yeah, this ranks me on the... Actually, wait, is it first or is it slowest? First test, yeah, so it ranks me on a single test, while I think n equals 16 should be the most efficient solution on average. But it looks like 14. It wants 14 for this one. No, but you know what? I think I'm just gonna bite the bullet and I'm gonna say that I am making a generic solution, and a generic solution is gonna be 16. So asymptotically average best performance is gonna be with n equals 16. So yeah, I'll do that. Okay, so switch schematic, tailored storage cracker. Let me create a plus 16. There we are. Plus 16 costs 12 gates. Pretty cheap. And what I do now is... Oh no, I also need a plus 255. Be right back. Actually, I already have it. Minus minus. How is this so expensive? Oh yeah. Makes sense. Yeah, 255. I wonder if subtracting 1 could be a cheaper operation. No, I don't think so. Don't think so. But yeah, so what I want to do now is I will have a mux, like I described. I'll have a mux around here. And so long as the input is nothing, 0, we're gonna have the mux piping the first thing out. But then once the input gets to something, it's gonna be the minus minus, and all I do now is I just put a delay, I think. Put a delay? No, not a constant, a delay. Something along these lines. Oh no, it doesn't fit. Oh well. And the input to both of them is the same. Like so. And then I enable both input and output constantly. Let's see. Now this is kind of fun actually. If this works, this is an interesting solution. Was that actually efficient? I mean, yes, but also seemed like it took forever. 69 ticks. 69 ticks. That's ridiculous. I think if I put... I think it may be a case of we missed. We just about missed, or... No. How do I get 69 ticks? Or... Wait. What was it? Was it really 69? It really was. Nice. I just can't believe it. Okay, let's so 16, 32 I guess. 48, 64, nothing. 80. Right, we keep guessing until 240. Oh, wait. Wait, but this will take... This will never actually succeed. Yeah, if the answer is... Is that why I did 15? So that we don't... What? How did it just succeed? What the hell? Yeah, if the answer is 255, we're never getting there. And that's a problem. But how could it actually work? 239. Wait, what? Now it did. So 16. We start at 0. Wait, actually, do we? Do we start at 0? We don't. I start at 16 actually, which is a bit weird. I think I might wanna could I rewire this somehow? Yeah, I think I could do something more like this first of all. I want to start at 0. Yeah. So this, there, and down. Like so. Yeah, so now we should be starting at 0. However, I am confused by how this can work at all. We start at 0, but then we get back to 0, and we should just be looping forever. How on earth do we ever guess anything different? Or, oh, what? 200 and... I don't understand. At some point... 240? 0, nothing. How can this change? 76, 92, 224, 240, 0. 255 now. How did I get to 255 from 0? I would need a minus minus, but I didn't ever have this thing on. This is not doing anything at all for some reason. Yeah, I don't understand. Well, one thing I do understand is that this is a byte, but I did check at one point. This is, by the way, I don't think I ever show this, but if we take a byte and we pipe it into something like a 1-bit switch, for example, right? So if we forcefully extract a 1 bit from a byte, I believe it's the first bit. Yeah, it just connects to the first bit. See? So yeah, and since I expect the beep to be a 1, I expect this to be fine, but I'm still weirded out by why... How does this work? Okay, give me a moment here. Actually, I think my circuit is overall not exactly correct, and what I'm getting is a side effect. I haven't considered the time it takes between pushing an output and getting a response from the input. So if I try, let's take a look. If I just directly pipe, let's enable this. If I just directly pipe a large constant, like 255, right? If I now tick, right? This does not update immediately. This only updates on next tick after I have done the thing, right? So I kind of need to take that into account at least. So it's actually, I think I need more delay. No. Wait a minute. So this is interesting actually. I think what I might need is actually not a delay but a switch here. Wow, this is a bit complicated, right? I want to, before propagating to the next step, I want to actually take into account my feedback. So I guessed, right? So right now, let's restart. I guessed. Then I want to wait. So I actually, yeah, I think I want my guess. I think I want my guess directly propagated into the things. However, the decision on the next guess should not be made immediately. The next guess should not be made immediately. It should be made not on the next tick, but the tick after that. But if I just put 2 delays here, right? If I were to just put 2 delays, it wouldn't actually influence this value. All right, this value would be the old one. And that's not good. I would have a weird situation. So I think I actually want a switch, and I want the switch itself delayed. Somehow. This is interesting. Okay, give me a moment here. So here's a thing I came up with. It's weird, but this is actually, interestingly, the kind of thing I would expect to be struggling with when trying to create customized circuits. This is part of a, you know, control flow clock thing, where I need to make sure that I do things on the nth tick. So what this does is this is just an example. So I have a counter and it ticks every tick. Of course, it ticks up. But what this thing does is it only probes the input of the counter every other tick, and in between the information is just discarded. So what we'll have as the output is just the even numbers. So we have 0 right now. That's the initial value, right? But now this 0, even though the wait, where's the counter is? The counter lags behind a little bit. That's weird. I'm not happy with that. But this does work. Still 0. Then we get a 2. And it's still 0. Wait, does it? Yeah, I think it needs a couple of ticks to just prime itself. But then we're putting out a 2. This is from that one. But now the input is a 3, which is junk. And I do not want it. So instead what I use is wait, this is so weird. I think I may have built... I don't know what I built. It works, but it's not... I don't understand how. Right, so you can see what it does, and you can see what I'm going for. Right, it increments by 2. And there's no 51 at any point. It remembers the last output it got. And then it only updates every other tick. But I wonder if this could be simplified, and if this is even correct, and this is awkward. Okay, give me some more time, I'll be back. No, this does actually work, and this does work for what I'm trying to do. Honestly, this is not entirely clear to me how it works. It's very confusing. I find myself very confused by these ticks and the delays. What the 0th tick is, like the first thing. So right now I'm looking at a state, which is a legal state. But then when I tick once, then something happens. So is this tick 0 or tick 1? I think it's tick 1, and I'm just constantly looking at tick 0. And yeah, these things, my brain just cannot understand them. But this does work, and it does work in the way I intended it to work. And this actually solves the problem in a reasonable way. So we take all the way up. I think this still does have the problem of 256 with overflow, but I'll talk about that in a moment. It just so happens that here, the actual, so once we get to 240, right? We just guessed 240, but now we need to wait for this guy. And that's what we do. And the answer is actually below 240. So now we got this guy. And now this mux works. We get the 239. And our next guess is actually 239. We do not overflow to 0, even though we kind of did here. That signal never got through. And then we do... Excuse me? I thought you just worked. Well, that's embarrassing. I literally, I'm pretty sure I just witnessed it working. 239. Yeah, 238. What? Did you see that? Or did I accidentally press the reset key? I think I may have. Yeah, so 237, 236. Right, we wait for the update on the output. And then we're done. So this is I think about as good as it gets, 60 ticks. However, this does have a problem with overflow, because if my solution was, for example, 255 or even 241, I would never reach it. So that's a problem, and I think what I actually want is I want a multiple or a number that divides to 55. I think I'm going over the exact same reasoning I did in my original video. So does 255 divide by 15? I think it might. Let me check. Yeah, 255 is divisible by 15 and it is 17. So I'm just gonna use a plus 15 element. Be right back. Done. So sorry for duplicate content. I think I've already done all this and I've already divided 255 by 15, but oh no, I wired it wrong. BRB. Fixed. It was a stupid mistake. So that's gonna be my solution. And this is an interesting setup. I think I might need the generalization of it eventually if I go for more complex solutions or solutions to more complex problems. But for now, I think I'm gonna proceed and I'm not gonna try to figure everything out exactly. So let's take a look at what else is new. What else is in store? Yeah, we're improving our scores quite a bit, right? 1.6k versus 200. Masking time. Let's see. Calculate modulo. Well, I might just have a component for that, I'm afraid. But it's actually not even... I don't even need that because modulo 4 is a bit operation. I don't need div mod, so mod 4. I do not need div mod at all. I think I can get it in gate score 0. I actually can get it in gate score 0 and tick score 1. This is gonna be my most efficient solution ever. So mod 4 is just these two. And that's it. And I need an on for IO. This is mod 4. That's it. Gate score 0, delay score 0. Okay, let's see. I want a Steam achievement, honestly, for a solution with with the lowest score possible in the game. Okay, sure, cool, onwards. Wait, yeah, so now all we have left is the maze. Okay, and the maze is much more complicated. The maze is actually an interesting program, which is gonna be, yeah, this is gonna be difficult to implement. So let me consider this for a moment. Right, here's what I'm thinking. I do, like I said, want to implement an improved version of Overture, just clean it up because this is a mess, and I want a nicer thing. Now, obviously, I could just apply leg to solve these issues, to solve all these problems. Leg is strictly more powerful than Overture, strictly more expressive. I can do more things with it. But I think there is merit to using a small thing, and the idea is, the first thing I'm going to do, I intend to do right now, hopefully I can create a whole new architecture in the next 20 minutes. I think I want to keep the specification of Overture, make a new architecture that will implement the Overture instruction set, and use that to solve this maze problem. So that would be the first step, and then once I'm done with that, I can try to make a specialized circuit for the maze that is not Turing Complete, but just solves the maze. And by the way, I looked it up, and what this is called is not tailored. This is called ASIC, right? Yes. Application Specific Integrated Circuit. So these are going to be application specific integrated circuits. Fast forward half an hour. I have now completed a more streamlined version of Overture called Act 1, but that will have been the previous video. Yes, time flows weird on YouTube. And right now, jump cut to more ASICs. Yeah, I think that'll be about it, and I'm ready to start working on a application-specific circuit. However, I just realized that before the maze, there actually was another problem we solved, which was Spacial Invasion, and it looks like it's not scored, so I've been ignoring it so far. But I think it might be a helpful intro to building specialized circuits, because these have been completely trivial mostly. I mean, I guess Storage Cracker was slightly interesting, but I expect the maze to have fairly complicated control flow. And I think doing Spacial Invasion before proceeding with that might be helpful. So yeah, it was this one. And what we did, right, we did this, wait, shoot, wait, shoot, wait, shoot. Let's see if the program actually still works. It doesn't. Oh, why? Okay, let me figure out what's up with this. I'll be right back. Right, I fixed it. It was actually, the program was still correct and the program was working, but it's the overture that was broken. I completely reverted the entire schematic back. This is still overture, as you can see. And this is the old program and it works. But actually, this program was slightly inefficient. What I was doing in order to detect that I'm not seeing a rat was I had a rat saved. And what I was doing is I was observing and waiting for a rat. And I was subtracting the rat from my observation. And instead what I could just do is I could just wait out zeros. So that's what I did in an improved version of this for Act 1. Yeah, this is a minor improvement, but yeah, it's essentially the same, except instead of waiting for a rat, I wait for see nothing ending, right, for the end of seeing nothing sequence. Which actually, I think this should free up, yeah, this frees up a cache register for me, so I'm gonna fix that, improve that real quick. Yep, no longer needed cache for rat, so now I could improve this slightly. This saves me 1 tick, but that's also cool. So yeah, now we have this new solution that works for Act, and it is pretty pretty small, and pretty efficient, actually, pretty fast, which I should use. Okay, be right back. So this is the program that we have, and I think what I am going to do initially is I'm gonna try to, the same way I did for div, I'm going to try to implement a, I keep forgetting the name, the special ASIC, application-specific integrated circuit that directly implements the program. So for that, I'm going to open up this thing. I'm gonna save my program here so that I can see it without opening the assembly editor. And now we're gonna create a new schematic, call it rats, because these are supposed to be rats actually, these things. And let's see what I can do here. So first of all, I don't think, yeah, I'm pretty sure I don't need any cache. because I can just directly output my things. And what I'm going to want is, yeah, I don't need to remember the rat, which actually I don't need the rat there either. Well, I'll clean that up. But the first thing I think I want to do is I want to plop down all of my actions as constants. So I'll have left 0, step 1, right 2. So I'll do that. So these are all the constants I'm going to need. I need left, step, right action. The other ones, such as poo and chill. Actually, oh, no, I do need... Wait, no, I was thinking about the maze, and I implemented only the instruction needed for the maze. Okay, this robot needs some more. Be right back. Okay, these are all robots' instructions. And so these I should be able to eventually just pipe into the output through some clever circuit. So what do I want to do? First thing I want to pew, then step, 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 step. And then I want to do loops. Okay, so I'm thinking... Huh, this is an interesting, because I'm immediately tempted to use a counter. Like, literally a counter. I'm not so sure that's gonna be the best idea. But, well, it is probably going to be the simplest, as it is going to be close to an actual architecture. So... yeah, how many instructions do I have here? I have 1, 2, 3, 4, 5, 6, 7. I have exactly 8 instructions in my loop, which is interesting. That's gonna be fairly neat for a 3-bit decoder. I'm immediately thinking of a 3-bit decoder, of course. But how exactly do I handle the prep phase, the pew now and the initial steps? I wonder. Well, okay, let's try, how about, I should probably try doing something simple first. So, something I can do is I can put a mux. It's just a single mux. And it's going to be a pew first. And then it's going to be a step on all subsequent things, on all subsequent ticks. So what I want is I want a single delay, which will allow us to do the first pew. And then, yeah, so this should be the first part of the prep phase, right? So we pew. I see no pewage. Oh, of course. I think I'm gonna be constantly outputting. I think this is even correct, pretty much. Why 5? Oh yeah, because 5 is pew. Yeah, so pew and then step. But then I need to stop. At some point. At some point I will need to stop. So after the prep phase comes... I wonder if I should use muxes or if I should use a decoder board. Well, no, I do intend to use a decoder board already, but for now I think this is fairly intuitive. Yeah, but the question is now, how much is a delay line? A single gate, right? So I think it should be fine if I just... so how many delays do I need? 1... Oh, I don't know. It's honestly kind of easier to just test it. 1, 2, 3, 4, 5, let's say 6. And let's see if this works the way I want it to. Come on, just about fits. Okay. Let's pointless, but whatever. So let's see how this goes. And then, yes, perfect. This is perfect. So once we reach the destination, this mux will always be on, so we can completely forget about all of this. And now we just need to think about the loop, and we need to pipe the loop out into this mux, into this pin. So this is basically my new output, right? So for this, I think I do want a decoder, and I probably will use a counter for now. So let's okay, give me some more space, please. Give me... Let's just use the regular game-provided 3-bit decoder. Or, what's it called? Abductor-provided 3-bit... Wait, what? Oh, we had a 2-bit decoder all this time. I didn't realize that was a thing. Honestly, I kind of feel like it... Was it added in an update? I don't think I've ever seen this thing. But, okay, so... I want this split. I want this split, and I want it decoded. Oh, no, it's not. No, it's not this that I want split. What I do want split is I want a counter. Right? So something along these lines. Oh man, except the counter will start counting at the very start. Can I prevent the counter from... Oh no, oh no. Actually, I kind of can, right? If I just do a not here, I can disable this counter for start, right? Yeah, it just keeps being overwritten by 0, and then it starts counting. So now we're at 1. Okay, something along these lines. So now what I want is actually these 8-bit switches are just switching the however many 3 bits of this instruction. So I could reduce that as well. But for now, let's just use full switches. So how many? 1, 2, 3, 4. Perfect. Okay, let me make a board here. Right, so we have 8 instructions. Determined by counter. I think this is fine, and actually I don't think I might not even need... this is complicated, because this counter, because I only take the last 3 bits, it's already mod 8, pretty much. So this final loop will just automatically start to its jump to its beginning. I won't need to do anything clever about that. But I think that only works if I had exactly 8 instructions, but now that I don't need this as an instruction, I actually have 7 instructions. But we'll see, we'll see. So yeah, what I want now is I want to chill, right? The first... I'm not even sure this will work. We'll see how this breaks. First I want to chill. That's the first thing I do. Then I need to observe, and that's interesting. So ooh. That's not, yeah, these are not, I'm not doing 8 actions. I have 8 ticks. But I'm not performing 8 actions. I just realized it. Right, these suppose that I always do something, but in fact, there's quite a few moments, well, actually there's 2 ticks when I don't do anything. Well, it's kind of, I think it's just for now, it could be fine if I just Oh man, this is difficult. Give me a moment here. Well, okay, no, this is not I can just I can stop thinking about assembly too much and start thinking in wire terms, in hardware terms. And really, this load input and then jump if input is 0, I can do in the single tick, right? I can just take the input, which, by the way, I'm constantly... I think I'm also constantly loading inputs. This is probably not true. I'm not constantly pushing outputs, although... Maybe, yeah, probably. That's probably the case for all integrated circuits, actually, because whatever might need multiple ticks to calculate in an architecture, I can just make in one tick using my specialized circuit, application-specific circuit. So yeah, so what I do here is I have this thing, and I need to check that it's equal to 0, for which I already have a custom component, right? I have a not equal 0. Do I want to add an equal 0? So let's see. I will want to overwrite the counter with a 0 if this thing is 0. So I want this enabled. I want the override enabled. Yeah, so I think I do want not equal 0. Here. Probably. Right? Is that right? Not equal 0 means... No, not equal 0 means I'm seeing a rat. Yeah, I want to override when it is 0. Well, let's just... Again, let's experiment. Let's not worry too much. So I want an OR. That's fine for now. Let's plop an OR down. Do this. Add a not. So not equal 0. This is going to be equal 0. So let's see. I get out. That's fine. I'm observing 0. Yeah, and now the important part. Yeah, I'm outputting a 3. I'm chilling. But now I am seeing a 0, so I'm still chilling. Why am I still seeing a 0? Why is the input 0? What was that? Yeah, it's so... The time is so confusing in this game. I don't know if it's me or if it really is the game or what. But like right now it says seeing 33 space rat. But I'm seeing a 0. So like... I'm assuming I'll see the space rat next tick. Yeah, so I have chilled for one too many. Oh man, and also the counter didn't increment. Oh, time is so confusing. I hate time. Time sucks. We need more timeless physics. Yeah, turns left, which is not too bad, right? Yeah, it's because the thing starts actually doing something and it gets to zeros here and here. Yeah, but these delays are so difficult to deal with. I need to think. Okay, my brain is still not accustomed to this and I'm still a bit confused, but I think there is basically a lag in robots' perception. So the way I feel is natural to think about this would be to consider this literally, to consider this thing to literally be inside the robot's brain, and for this thing for the input to be connected pretty much to the robot's eyes. And so the robot sees something. That's your input. It crunches the numbers. And this is the output. And this would be the robot's response to what it's currently seeing. Right? So that would be the next thing it does. But that simply isn't the case. So right now, when we start, and I think this has to do with tick 0, like before I press anything, this thing right now, I'm already telling the robot to do something, but it's not yet seeing anything. Right? So what will happen is the robot will do the thing, and then what it's currently seeing, what the input tells us, is 40, which is what it saw in the previous state of the world. So right now, seeing create 40 before we should, right? So that's what happens. And so this thing just lags behind, the input lags behind, and we need to allow for a tick for it to update before we do an action, if that action is input sensitive. So I think I should be able to do that without too much trouble, at least in this kind of inefficient setup. So what I do is I get rid of this for now. Right, this is not correct. I do not always want to immediately act on my inputs, and that's what I had. But instead, I can use this decoder as a pacemaker, right? Which it is. It's literally what it is. But instead of now outputting on every tick, I am not going to be outputting any value here. And on the second tick is going to be a bookkeeping tick. It's going to be a tick where I load in the information, analyze, and maybe jump. Right? But if that's the case, then I need this tick to not have an output. So now I cannot use this on. But I think it's, yeah, and I can decide basically on which ticks I want the thing on. So right now it's just this tick, and yeah, this happens to work for my initial state, because my initial state here is with this on with the first bit. So this is still going to work for the init phase. No, why? It was supposed to work for the init. Oh, it's because, yeah, I don't have the not connected. It will be connected somehow, but I just disconnected it for now. Yeah, so the init phase is working. But now, on this tick, on this point, I do not have an output like we discussed. And instead, I use this thing to make a decision. At this point, when this is on, I may want to update my clock, my counter. And when I update it is decided by the input. So I need the input to be 0. If the input is 0, so this, if the input is currently 0, and we are in tick 2, so we are waiting for an input, then we will update. So this is literally an AND of tick 2 and input 0. And with this not, I do an OR. Just fine. Just the way we had it before. And I think this should actually work. So let's see. Pew, I go up, 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 up. And now what's happening? So let's take a look. Right now I am outputting chill, right? That's going to be the next thing I do. I'm going to chill, but actually I think I'll chill again now. Yeah, I'm chilling again. That's not good. But after that, let's just see. Oh, actually, no, I am not. Look at this. I am not chilling again. I have just chilled. Yeah, so what this outputs is kind of what just happened and not what will happen. Yeah, so the input, yeah, so both of these are kind of talking about the previous step. So I have already done my previous step. I have already seen the 0, and I have already done this, which is nothing. But yeah, we're now at second tick. And would you look at that? We are now both seeing a 0 and we are ready to jump. So we jump. And this will reset us back to chill. So we should chill again. Oops. I think it reset. Let's see. So right now, we should chill. No, we look and then we chill. And now we look, but we do not start chilling. And instead, next tick is gonna jump to the next thing. Right here. Yeah. So, and this just needs to be pew. So let's just try this real quick. Let's try pew, pew, pew. I need to shoot 4 times. 1, 2, 3, 4. Just like that. Let's see if this works. So I walk up. I chill, chill, chill. Yeah, I load, chill. And now I will process for a second. I have processed the rat. The rat is not free, so the rat is not empty space, so that is a rat. So I am proceeding. And I should pew now. Oh, except I need to... Well, yeah, I kind of don't need these switches, really. I only need 1. And what I actually want is I want 4. So I don't need this many. Yeah, I don't need much of this, really. What I really want is a huge OR, right? So I want an OR of this, this, and this. Right, so let me OR them together. What's it gonna be? A triple OR into an OR. Should be fine. Something along these lines, just quick and dirty, quick and messy wiring. Oops. That's not right. Okay. Bring this up. That's more like it. So this is my pewage, and this is gonna pew 1, 2, 3, 4 times. But also I need the output enabled, and this is also gonna be an OR for now. I realize there might be improvements to this. So yeah, I'm pewing on this. I am doing a thing on this tick, and I'm doing a thing on these 4 ticks. So let's see if this works now. So chill, that's weird, but we'll let it be for now. And now, process, and pew. Pew, pew, pew. No pew happened. I don't think. Or did it? I think it did. Yeah, there was just no sound. Yeah, it's the thing reset. Wait, no pew happened. Why not? That's weird. Why not? 1, 2, 3, 4. 1, 2, 3, 4. And I need 4, right? Yeah, I need 4. Why did it not pew? I don't understand. So, pew, pew, pew. And then this one? Why would this one? Oh, it's because, of course, I connected this wrong. That's fine. Easily fixable. So now, walk up and pew, 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 pew. Done. And I think this might actually even literally just work. Because we'll have enough time for this thing to get back to 0. And once it gets back to 0, it will start this part again. So I think... Haha. Yep. We just solved Spacial Invaders. However, this is very unclean and untidy. And I do wonder about the jump. Could I jump earlier? Yeah, I mean, I could have another thing over here. This would be my next tick. And actually, it would be... it would actually be just this. Oh, yeah, that's all. I just need the triple ore. And I pipe this into there. And on this tick, once I reach it, I just reset. So, let's see. Success. And I think this is even tick perfect. Pretty much. Yeah. Kind of. No, maybe not. I don't know. I am a bit worried about this first chill though. Why? So once I reach here, I expect to load the information into my brain. Yeah, but the knot is still on here. Wait. What? So do I need it like this? I don't know. Let me just check. Oh, yeah, like... Come on. Like this and like this, perhaps? So I need to start... I need to start the counter a bit early. So let's see again. I reach, and now I need to start looking. Yes. Chill. Look. Chill. Look. Chill. Look. Pew. Look. Oh no, pew pew. That's fine. I don't need to look. Yeah, look, chill, 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 look, chill. Yeah. And then look. No. Yeah, look, chill. Look. Pew, 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 pew. Yeah. Okay. Alright. Let me give this some thought and see if I can optimize this, or more importantly, this is a mess. This is a right old mess. And I wonder if I could see some patterns in it. Like, instead of using these custom ends and ors and everything, if I could perhaps see something. Yeah, and I'm also wondering if maybe I could get rid of this. And I could reset to say well, I don't know. This is... Yeah, there's a lot left to be desired here. Okay, give me some time. So the first thing I'm thinking about is replacing the counter with something else, because the counter seems like overkill. And this is the first thing that came to mind. So the NAND here, the part before the NAND, is a single tick pulse generator, right? We get an on, and then once this updates, we will never get an on again. So it'll just be one on the first tick. So now if we put a line of delays to it, we'll just have one thing glowing at a time, right? So boom, 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 like this. And this is this can work, I think. I'm pretty sure. We can emulate a loop like this with a literal loop, but it's not actually going to work because, yeah, this is going to short circuit. And it's either we need an OR here. We need ORs everywhere, like, you know, this. And then the output is this. Right? And then boom, same thing. And it keeps looping in this loop. Which actually I could like I could make a custom component, for example, which has an OR. So it would have two inputs, you know, one input on the top for a loop. And it would cost 2, and I would build chains out of them. But that actually seems kind of expensive, to be honest. Considering the fact that really a counter is not that expensive, a counter plus a decoder. And I'm not sure which is actually going to be more efficient for which program size. By program size, I mean how many instructions we need to perform. So here, pretty much, we have something like 1, 2, 3, 4, 5, 6, 7, and then 8, 9, 10, 11, 12, 13, 14. Something like 14 instructions we have, 13 different ticks. And the thing is, if I have only 13 ticks, I could use a specialized counter that only counts up to 16, right? Which would allow me to reduce the size of the adder. And basically, I think 16... What's 16? Actually, even up to 15 is enough. So it's 4 bytes. And I think this would literally cost half. And by this, I mean, while here we do use only 3 bits, I mean replacing this entire thing with a counter as well. So that would need 14, so 15. So that would be half the cost of the counter, which would be like 25. And this decoder would still need to be there. Actually, we would need a larger decoder, which I do have. 4 decoder. Yeah, that's 28. I mean, it does look more expensive. So it's going to be 25 plus 28. Pretty much. So 50. And this would cost 2 per tick. And not even that. I would only need custom small things for ticks which I need to loop back to. So this kind of architecture makes labels cost money, right? In order to return back. Basically what I need is I need to plop down a label here, and the label is the OR. Right? This is a label. So that's my first thought of how I could probably try to generalize the idea of the counter. I'm still not sure whether this is better than this, because this is counting in unary, and there's no way counting in unary is more efficient. But also, maybe it is more efficient for smaller numbers, and then for large numbers you want to use a decoder or a counter plus a decoder, right? Because this would take size log n, while this would take size n. Okay, so that's one thing. The other two things are, I am thinking about how to generalize this decoder board. Like what's up with these ORs, and could I do something clever with these switches? And also this part is another interesting thing. You know, the input and the decision on when to actually jump. Which... How would I... Okay, that's another question. If I have... So let's say I do have a jump. So let's put... I do have a label for now. Right, and I'm prepared to jump here from here conditionally. Oh, yeah, I would need a mux, right? I would need a mux to decide where to go next, down or up. Right? Like, do I go here or do I go here? Is there a 1-bit mux? There isn't. There is a decoder. The decoder is not exactly what I'm looking for. Do I not have a 1-bit mux? I thought I made. No, apparently not. Okay, let me think about this for a moment. So I decided to experiment with this idea a little bit, and it all just immediately fell in place. And this is actually a full solution. This works. It's very simple, and I'd say it's pretty elegant, actually. It's even simpler than it looks, I think. But I guess let me walk you through some of the changes I made. So first of all, let's discuss this part. Pulse, I made some custom components. Pulse is the same thing. It's just creates a 1 tick signal, right? So on the first tick it's going to be on, and then it's off forever. So that I can use with. I made a custom component that is a tick. There's a bunch of versions of it, but those are just reductions of the main thing where I don't need some functionality. But really there is one main thing, and it's this. So this is exactly the same as just, the basic functionality of this is exactly the same as a chain of simple delays. So see, it jumps, and these are ticks, right? So tick 1, tick 2, tick 3, tick 4, essentially. That's what happens. However, an additional functionality of this thing here is the fact that it has 2 more pins. It has this jump and jump 2 pin. And what this essentially allows us to do is we can, for example, if we want to jump from this tick to this tick, I can take the jump 2 and just connect it. And instead of ORs, I use gray pins, right? So it's the same basic idea as a bunch of switches connected to the same line, except they're not actually switches, they're just one-way things. So, well, I think this doesn't really require further explanation. It seems fairly simple. So I can just power this either from here, or it can be powered from here, and that's allowed because those 2 pins are both gray. So this allows me to jump back somewhere. It actually will allow me to jump forward as well if I want to jump there instead, if I want to jump over some instructions. And the other pin, which is just jump, is the thing that decides whether we want to jump or not. So when we're on, and if we take a look, so we are here. Let me add this tick as well. So we have these ticks. So this is what happens. We're on this one, then we're gonna go forward, forward. And then next, we would expect to get here, right? But since we are jumping, and we will jump back here, that's what happens. So we're back on here, and this will just loop forever. This is essentially a forever loop because we're always jumping. But this, of course, can be hooked up to any kind of condition. So that's the first thing. This is it. Like I said, there are some reduced versions of the thing when I don't need to jump, for example. So this is just gate score 1. This is just a wrapper over a delay, just so it looks uniform. But because I don't need to jump, I don't need to spend the extra gates. So yeah, this is our entire clock pacemaker thing, and it divides the entire machine, the entire circuit, into 2 halves. So this and this, these are logically pretty much completely separate. So I guess let's take a look at the bottom part first. And what we have here, this is essentially a full set of robot controls. So we have all the buttons we can press on the robot essentially to make the robot do something, right? So we can make the robot do pew, we can make the robot step, we can make the robot chill, and I can easily add something else. I can add action here, right? And just connect it the same way, right? But these are just the ones that I need for this program, so that's it. And they're all hooked directly to the output via switches. And again, I use the OR trick. This is the multiple things. This is essentially a, it's enough to power, if they are connected like this, it's enough to power just one so that the entire line lights up. And they're also literally pretty much just switches. It's this. So once I know that I want to output something, I also enable the output pin, the output thing, and it outputs something and something happens. So this entire part is the thing giving directions to the robot. And each tick, we can decide, do we want to give a direction? Okay, I guess we do. So then we bring a line down. We decide which direction we want to do. Do we want to poo? Okay, so the first thing we want to do here is we want to poo. And that's what I do. We have a one-way pin. Again, this is the same application of the same idea. I went a bit crazy with the gray pin ors. But all we need to do to poo is to power this line via a one-way pin. So that's what we do on the first tick. So that's we poo. Then on the second tick, we're gonna go forward, forward, forward a bunch of times, right? So second tick, forward, step, powered, again, step, powered, again, step, step, step. Then, we know that we have a free chill. That's actually an optimization I had in the original program as well. I didn't quite realize it, but yeah, once I get up, I chill without checking first. So I chill and then I check. It's a bit more efficient, I think. I didn't actually check. Yeah. So I chill then. And now, after I have chilled, comes the next part, the interesting part. Next, what we want to do is we want to perform no action. So you may notice that there's no line going down here, but instead we're gonna do a consideration. We're gonna observe and we're gonna think, and we're gonna think where we want to jump. And that's literally what happens. I color coded it with a different color. So this purple, whatever it is, enables the input first of all, and it's the same way, right? I have these one-way things, and if I wanted to do another check at some point, I would go up. So essentially you can think of each tick as either going down to perform some action, or going up to not perform some action, but instead think. And this one does not go down, it goes up, it thinks, it loads an input, and this input is piped into equals 0. So we check whether we're still looking at nothingness, right? Are we looking at nothingness? We are. And if we are, we're gonna jump back to the chill command. So we chill, then we load again, we check equals 0. Yes, we are equal to 0. So we chill, we jump back again, so we chill. Now we load again, we look, okay, now we're not equal to 0, we're looking at a rat. So this is off, and we proceed with the chain of command. And yeah, we just do 4 pews, and then this loops unconditionally, this loops back again to chill. And another thing I would probably want to mention is this piece of wire right here is essentially a label, and whatever connects to this label, this wire, is a jump to it. So these are both jumps to the same label, and different labels would be kind of different heights. So for example, if I wanted to jump to here, I would have another label, and then I could jump to it from multiple places, no problem. But there needs to be only one destination. Which actually... yeah, that would be... I think that's fine. Yeah, that is fine, because I am not jumping directly from a tick, but instead I'm jumping from a separate pin, which does not influence anything else. So jumping from somewhere does not influence anything else. If that even makes sense. So yeah, that's it. And I think this is actually a fully generic robot control circuit. One notable thing this lacks is an ability to perform operations which involve memory. So this is, in a way, kind of stateless. This is kind of a dumb algorithm that just makes decision based on what it sees. And it keeps its state separate in the actual game, kind of. And you know, we have no registers here, and we can't remember anything other than, I guess, we do maintain a state in terms of where we are in the program. But for anything that doesn't require saving values, I think this must work, and actually think I should be able to very quickly and very easily implement the maze using just that architecture. So let's make a new schematic. Let's call it, actually let's copy this. So rats, this is the original. You know what? I think I might delete it. Yeah, I'm literally just deleting this. Rats. Yeah, rats 2 is now rats. And rats 2 is not gonna be a rats 2. Rats 2 is gonna be maze. So let's switch to maze. And okay, let me open the program. Okay, this is the implementation of the maze, which I had for Overture. And the first thing I'm gonna do is I'm gonna completely reset everything here. So I keep the bare bones structure of the machine, but I will need to kind of load a different program into it, right? So these stay mostly. Still want stuff like this. Yeah. So now the next thing I do is I need to, well, let's first set up the commands we will need for the robot. So we won't need to poo in the maze. What we will need to do is we will need, so first of all, we'll need a step. Let's load a step. Actually, already, well, whatever. We'll need a step, we'll need a left. Yeah, I know these switches, by the way, these switches are a bit wasteful, but I decided to keep them, at least for now. It doesn't, it makes it neat. So we'll need a left, right? Then we'll need a right. That's the next thing. But it looks like we're gonna want more, because we also want, we don't need observe, because observe is... what even is observe? Why do I have observe? Yeah, I think observe is not... I think observe was an alias for taking an input. We won't need it. What I do need, however, is I need action. So what I'm gonna do is I'm gonna add another layer over here, and I'm gonna put action, right? So that's another thing we can do. Okay, now let's see what we're doing. So the first thing we're doing is we are doing a step. So first tick, step. I don't like how this is. First tick, step. Except I want a one-way switch here, a one-way wire. Next, we want a left. We're gonna want... oh, come on. We're gonna want a left. Like so. We're gonna want another left, right? We want a left, right? Then, let's not worry about jumps for now. We will want a right. So it's literally all the commands are just put in here in order, as it would be with assembly. So we do a right, then we observe that's nothing. Actually, no, the observe, so this is another part of the puzzle. These were all actions. We had step, we had left, then we had a right, but observe and go are not actions. Observe and go are gonna be a decision. So we won't have anything here. But then we will want an action down here, right? So that's an action. And now, what we need to do is we need to decide, we need to figure out all the jumps here. I just realized my pulse was a bit wrong, because we will need to jump to it, but it's not, it doesn't have a gray pin at the output. So let's switch that real quick. fix that real quick. I will want a gray pin here. Switched output. It's just like this, so that it essentially doesn't have an off state. Its off state is just gray. So that's it, right? Yeah, and here we will want to make a decision. I forgot to put a one-way actually connected, right? We will want to make a decision. Okay, we won't need any of these. That's all the instructions, right? So this is going to be very short. However, tick 2, yeah, that's fine. So from this is an unconditional jump, so I will always be jumping. And I'm gonna be jumping to search. And search is the point where I was doing a write. So write is here, which means this is my search jump, right? Unconditional jump to search, to write. However, at this point, I need to jump if 0. So first of all, I need to replace this thing with a more complete implementation. Tick, I think tick from should be sufficient. Those are, I'm not going into the details, they're just reduced versions. So from here, I will want to jump to a different label, and that label is going to be the very start. Right? We want to go to jump to go. So here. Why is it on? Yeah, that's fine. But I am not always jumping. I am only jumping when the input is equal to 0. So what I do is I take my equals 0 component, plop it here. Let's color it in like so. And I think this might, if I did everything correctly, this might be a solution, or the solution. Let's watch what happens. Okay, something's wrong. Oh, that's fine. I need another. See, I'm just trying to save a lot of gates here by making all kinds of components. So for example, this thing. Because it has a non-gray pin at the output, it's the cheapest, but this means you cannot jump to it, because if you try to override it, it won't work. So in order to jump to something, you also need a gray pin there. So I did that. I might also want a pulse versus a pulse too, but that's just saving gates. Yep, there we go. Simple as that. Gate score 65. I think this is cheaper than the counter. Not quite. It's not quite cheaper than the counter, but this is pretty cheap, and I can reduce this immensely if I replace these switches with singular switches, right? So I would save, what is it? Like 28, I think? Yeah. I could save 28, and then I will be cheaper than a single counter to solve a maze. So let's, you know what, I'm gonna do that, and we'll see just by how much our score improves. There we go. This particular problem is also lucky because it does not require any conflicting numbers. So we have a step, and it exclusively enables bit 1. We have a write, and it exclusively enables bit 2, and we have an action, and it exclusively enables bit 4. So I was just able to make these intersections for free. But normally, if I were to have, for example, a left and a step both enabling bit 1, so for example, if both left and step were odd, that would mean they would both need bit 1. That would mean I would need 2 one-way things here, so connecting to that. So that would cost a bit. But overall, we can now see that our gate score is 33, our delay score is 12, and I'm pretty sure this is a complete solution to this level. Real quick, let's take a look. Our previous score was 594, and the total was 5k. The tick score is still gonna be the same. It's actually, yeah, it's gonna be essentially the same. Still gonna be 4k, and all I'm saving is the gates. But this is, I think this is still very cool. This is very minimal, and yet it's pretty universal. So let's run it. Yep. First try also. I didn't even have to debug anything. $2K. Looks like we did save a bunch of ticks. But the gate score... 33 gates to solve a maze. Oh man. This is... I'm very happy with this. I could even save one more. Actually, no, I couldn't. Yeah, I probably could try to figure out an even further reduction. For example, there is something to be said about repetition here. But it is... Right, so instead of having two of the same thing, costing me twice the same thing, I could have something more efficient. But this is kind of the same question you run into when you need to do, for example, when you need to do 15 steps. Is it cheaper to implement a loop up to 15, or is it cheaper to hard code 15 steps? Well, the 15 steps will be cheaper in terms of ticks, but it will be a massive program. So I'm not sure how that influences the gate scores in this kind of situation. But there is still something to be said about that. But yeah, I'm not going to go into that. And this is where I'm going to finish this video. Ah, so cool. 33 gates. Unbelievable.